Let's get started. Sorry, I had some display problems. All right, so peer review assignments will come out maybe today. We were waiting for everyone to get submissions in. We might, there were a lot of, the commits were a little bit more, it was good in that people did smaller commits and then pushed them, but it makes it a little harder to review the pull request. So we might send out some instructions about that. You can actually do, pretty easily, you can pull up the file that they ended up committing and get a link to a particular line and comment on that line. So we might just have you do that. You know, it's separate, just here's a link, here's my comments on that line, rather than trying to comment in line. But we'll send out instructions about that. Homework 2 will be out next week. We might even post it this weekend, but it's unlikely. Trying to get the TFs to review everything and get everything in place. Get Cython installed and working for homework 2 early, all right? Especially that test repo that I posted. Clone it, try running it. If it fails, let us know why. On OS X, well, I'll talk about that on the next slide. Did people, okay, question, Odyssey accounts, RC accounts, did people get email about this? Good. We'll need those later. Yeah, Harvard Computing, Research Computing, something like this. You got an email that said, here's your temporary account. We'll need that later. They have GPUs on the cluster there. That's often the easiest way to get access to a GPU machine. You probably, I mean, OpenCL runs on regular machines as well as GPU, but we want you to be able to compare them, and that's an easy way to do that. No class Monday, and the reading on Piazza for Wednesday. We'll discuss that on Wednesday. OpenMP on OS X. So on Linux or using the VM, you should be basically set. If not, let us know. Most of you seem to be running OS X. If you're using Homebrew in particular, oh, that's wrong. That should be in, let me just fix it here for the record. If you're using Homebrew on OS X, this is the easiest way to get an OMP compiler, of an OpenMP compiler. Clang is actually the default, so when you call GCC on OS X by default, you actually get Clang. It's just a different compiler, but it only added OpenMP a few revisions ago, and so this is the easiest way to get them. The script that we put out, the test repository, searches for that compiler, and we'll use that if it's there. Let us know. Try running that test repository. If something crashes, let us know soon, because other people are probably having the same problem. We can help you debug it. It'll make everything much easier in future homeworks if we know how to set up your basically how to detect which compiler you have and make it available, okay? So if it doesn't work for any reason, post on Piazza or send email to staff, let us know, okay? All right, using OpenMP in Cython. First, why? Why do we care? We have access to threads in Python, but they're Python threads, right? They're limited by the GIL. We don't actually execute multiple threads of Python computation or interpreted Python at the same time. Cython lets us get down to the low-level C code or get down to low-level C code and gives us fairly easy threading capabilities via OpenMP. OpenMP gives us C-level, very fast, native threads and locks. Doesn't give us anything like queues or anything like that. It basically gives us threads and locks and some nice syntactic sugar to stitch them together. Has syntax level support for parallel constructs. So if you remember back to the seminar by Charles Lyserson, where he talked about Silk and how it's very easy to take a C program, add some Silk directives, or a few Silk keywords, get a parallel program out. OpenMP is the same thing. In C, it's primarily in C and Fortran, or implemented there. In the compiler, it just uses pragmas. Pragma is this sort of, it's not a define, it's sort of hints to the compiler. Those just turn into comments when you compile with a non-OpenMP compiler, so your code is the same. And if you have the serial elision property that Charles Lyserson talked about, if you take and remove all the pragmas, you get the serial program back. So if your algorithm is correct, which it should be, if your algorithm is correct when you just have one thread running through it, and ignore all the parallel parts, then if you just remove all the pragmas, your algorithm should still work. It may not, that doesn't guarantee that it works when it's multi-threaded, it just means that you didn't screw up the basic serial algorithm. And we use OpenMP. OpenMP is simpler than library-based threading like pthreads or the Windows threads or things like this, where you have a lot more control over which threads do what, when, and you can split off threads and send them on wildly different code paths very easily. But you also have to do a lot more work to use those sort of threads. So this one gives you a few very simple constructs via the compiler, a few simple basic locks and things like that, and you get most of the parallelism that you need. If you have a much more intensive task that requires independent threads doing all kinds of independent things, then you have to approach it slightly differently. But in general, this is fine, especially for dense image computation or, well, basically anything where you just want to split up work. All right, so the OpenMP model of threads is, again, like Silk or a lot of other things, it's basically just a fork join model. You have a master thread coming along, just the standard serial program. Enter some sort of parallel region, and we'll talk about what causes that and what those are. Splits into a number of threads which do work, and then they join back together into basically, most of the threads just go to sleep. Thread 1 is the master thread. These threads just go away, they die, or they're just put in a waiting pool until there's more work. Serial section goes along again, forks into a bunch of jobs, they work, they come back together, and so on. So a lot of threading models use this. It's fairly simple. Again, you don't have the ability to have a single thread, at least within OpenMP, you don't have the ability to easily just create a thread over here that goes off and does anything. You know, you can't set off a reader thread and a bunch of compute threads and whatever else. But you can still get most of the things done you need to here. They're very lightweight, so it's not expensive. You know, it's going to use the operating system at the bottom. Creating these threads, these groups of threads to do this parallel work and then joining back to them doesn't add a lot of overhead. So it's not a problem to do it this way. All right, in Cython we get at these parallel regions via two tools. The parallel block, which is basically this parallel call, or, well, with parallel, and a parallel range. We'll talk about both of them, but the block first. One of them is just do a bunch of things in parallel. One of them is do a loop over some index and assign it to threads in parallel. Okay. Parallel blocks, they're basically just this. You know, going along, create some number of threads, split them off, do everything in parallel, and go on. So everything within the block is called independently. And depending on how many threads you say, that's how many times it's going to be done. Okay? You don't have to specify the number of threads. If you don't, it'll choose something reasonable like the number of cores you have. But then everything that happens here will be done in independent threads of computation multiple times. Okay? Actually, you can see what this looks like. So I've got some simple file here. This is the one that I sent out earlier. Bunch of setup. The way you get at the parallel is you import from the Cython parallel module to get parallel p-range, and then another function you can get thread ID that we'll use down below. Don't pay attention to the locking right now. So this is just the example I showed there, wrapped in a Cython function with some extra definitions. But the main thing is here, I've got a parallel block. I'm going to grab a value, and I'm going to print it out. All right, and I'm instantiating 100 threads to do this. So when I go over here, okay. Okay, 100 threads. If you run something, just even a printing loop like this, you'll actually be able to see that it's, in general, seems faster than the Python threads. The responsiveness is more, and they switch a lot faster. Okay. One thing to note, if you assign to a variable within the parallel block, it's private. It becomes its own, each thread gets its own copy of the value. okay? So val is private to the current thread. So when I do this, and I do some other computation here based on that particular value, whichever thread ID I have, or whatever I assign here, that value is local. It's not a shared variable. It's not, other threads don't overwrite each other's values like this. If you need to do something shared, you have to do it, you have to declare it differently. But in general, this is what it looks like, or this is how it behaves, okay? So you can see that already in what I had here, right? I pull out the thread ID into a value, I print it out, but when we looked at the output, everything, right, every value appeared from 0 to 99. So they aren't overriding each other's values, they get their own independent. Okay. What's that? They all appear, no, they all appear once.
Didn't you say that all the code underneath the tree has to be executed?
Yeah. Yes, but in parallel. So the value, basically each thread comes in. Let's look at the code. So it calls into the function. So when I do this, right, when I hit this line, I create a parallel block with 100 threads. It splits it all out, and each one only goes through here in a parallel thread. So each one executes once this value equals thread ID. Each one then tries to get the lock. That's just so that the printing doesn't overwrite each other. And then each one prints its value. But value is private. So if one thread sets it to 3 and one sets it to 5, they each see just their value. And then each one prints once. And we see, because it was 100 threads, the 100 values. Well, because, we'll talk about that later, but basically print is a Python function. I can't do anything with the Python runtime without the GIL, right? And the other thing is I drop it there. Do you have the code? You don't have the code up. Let's see. This is what happens if I don't grab the GIL. Okay. So I'll try to recompile. That's not good. The problem is here, well, all kinds of things start to happen. One, it can't create Python values to pass to Python functions. Even if I didn't have that, print would die because print is a Python level function. It's in the Python interpreter. And so to call into the Python interpreter in C code or in Python code, once you've given up the GIL, you have to get the GIL back. Remember, we talked about how saying no GIL has two effects. One is you're actually getting rid of the GIL, so letting other threads run in the Python interpreter thread, right? The other thing is you're saying that I'm not going to call any Python code within this block. So to call Python code, the first thing I have to do is reacquire the GIL. Does this make sense? Right, because otherwise I could have, I've got a Python thread, or I've got multiple Python threads. I can't draw them this way. They can't run next to each other. Right, I've got a Python thread and another Python thread, right? And they don't overlap because of the GIL, right? And so this one comes in here and then goes into some Python code, okay? So this is Python, and this is Python, or C, right? And suppose this one lets go of the GIL. Yeah, so it's no GIL, right? That allows this one to say, okay, well, I can acquire the GIL, right? And this thread can run while this stuff is doing multi-threaded programming, yeah? So this one is doing C code, but before this code can do something that requires the Python interpreter, before it can get back onto, in the Python interpreter area, it has to ask for the GIL, right? And to get that, this one has to stop. So this one either has to give it up, well, this one does have to give it up. This one will wait until this one does give it up. And so that's just what happens here, is it grabs the GIL just long enough to print, and then releases the GIL again. And then eventually, the function exits, and it comes back up to Python. But while it has the GIL, this thread can't run. It can come back here. Does this make sense? So there are two locks here, right? There are a couple of locks that we have to think about in this code in particular. One is the GIL, letting us get into Python functions like print, or if we wanted to allocate a NumPy array, or any of these functions, yeah? And then one is the actual lock to protect the print function which is the same as we saw in the Python versions of this problem, right? When we had the Python versions, if we printed out from all the threads, they would start to overwrite each other's output, right? This is the same, I'm solving the same problem here. I don't want to have multiple ones print out at the same time, so I put another lock, which is just my lock on output, lock on a shared resource, right there. Question? Do you have, oh, I see. So the question is, do I have access to the standard libraries of C? I do. Basically, I would just do this. Let me jump to the top. I think you can just do this. And then I could down here, I think that would give me the ability down here. Maybe for you, I have a better one. No, yeah. And then I think down here I would call, you guys. You like this? It's like pair programming with 100 people. I think down here, you can do that, and then I think you just call standard, you treat it like a Python module almost, like standard lib.printf, I think. I'll put it in an example later and update this, rather than trying to figure it out on the fly. But yeah, you can get it that way. You can also do, if you look at, you can also do tricks like this. C import. No, I'm not going to try to do this. You can do cdef from extern or something like this. You can basically import header files. And then you just give the types that the C functions take within there. And you get those symbols. So I could define the printf here or some other C function from a header file. And what it turns into in the Cython code, Cython, remember, takes your code here, puts it in C, and then compiles it. When you do a cdef extern or C import from extern, it just includes the header file and then uses the type information that you define there for the rest of its compilation below.
So, using the GIL here, does that break parallel nature what you're trying to do?
Question is, does using the GIL here break the what we're trying to do? Yes, if I were calling that, if I were trying to do something efficient here, it does. If, imagine this took a very long time. Right now I'm just getting the thread ID. But this computation could take quite a bit of time, right? Much more than printing. In which case, this would be fine. This would be done 100 times in parallel, except for I don't have 100 cores, but it would maximize parallelism in the computation and then grab the GIL briefly, and even this lock, right? The fact is that since I have no overthreads of execution in this particular problem, once I get this lock, no one has the GIL, right? Because we've all dropped the GIL. Every thread has dropped the GIL. So no one has it. I get a lock. This is a lock shared with all of my thread friends. I'm the only one who can grab the GIL. This is just so that the Cython compiler knows I can call Python functions now. Makes sense? So yes, in a sense, we have a serial block here. But no, also in a sense in that usually we would do a lot of work before output. Okay?
So how is this different in execution than when we're just using like native Python threading?
How is this different than native Python threading? The main thing is I don't have to create a bunch of threads in Python. Number two, this is at the C level, so it's more efficient. And I can give up the GIL in Cython and then actually run in parallel, right? If I don't have the GIL, then I'm saying basically I'm not going to call Python functions. There's no constraint that we only have one execution thread at a time, like we do with Python threads. Python threads one at a time. This lets us get rid of that. There are two ways you can mix these approaches. And we've seen that in, for example, the Mandelbrot code, right? Where we create a bunch of Python threads and then call into Cython, which releases the GIL. When it releases the GIL, other Python threads can go down into the code and run, and we get actual multi-threaded computation. In this case, we're dropping first into C and then going multi-threaded. And so it's more efficient. We don't have as much overhead for maintaining Python thread structures and things like this. Is that clear?
Well, and another thing with the OMP commands, are those kind of like just standard commands there?
They're not they're sort of special syntactic sugar that Python understands. Because in the C code, so I encourage you, if you have questions about what's going on under the hood, when you run Python, you can just run Python on an input file. You say Python plot.pyx, and it'll put out a C file. And you can look through that C file to see what it actually produced. And so I encourage you to do that. For things like this, it'll turn that parallel into a Pragma OMP or Pragma OpenMP parallel or something like this. So it'll insert into the C code the parallel Pragma. It says basically this entire block of code should be run in parallel with these settings. Okay. It's got a lot of extra noise. When you look through a Python output, it's thousands of lines long, but it can be useful to go in there and just see what's going on. Okay. All right, local variables. There is a warning here. It only works for C-type variables, so only declared variables. If you declare other variables with the GIL, it'll crash just because of the way that the way that the pragmas in the C code deal with private variables versus how Python deals with variables, where it actually allocates some space and does some things, and then when it goes out of scope, it has to free up that space. So you can't do this. So once you go into a parallel loop, you've got very limited abilities to allocate new Python variables. You can do things like what we showed where you print, but you can't necessarily do a bunch of Python code inside a block there. But you generally wouldn't want to anyway, because that's going to slow down your code a lot.
The way Python codes in C, is it like good? Like there's like this memory issue with C and
So the question, I'm not sure I understand the question. So you're asking how good of a coder is Python in terms of turning the Python code into good C code?
like in the management of the memory.
In terms of the memory?
Yeah.
I'm not sure which memory you mean.
When it's allocating.
Oh, like buffer overflows, like guards. Oh, so checks against buffer overflows. All right, so in a lot of the code so you're asking about how fast is it and whether it's safe, okay? In terms of, especially when dealing with buffers. So in the Mandible code, for example, and some of the other code you've seen, there have been some Python directives before the function that look like decorators. It's calling things like Python.boundsCheck and Python.wraparound. So by default, when you're dealing with NumPy arrays within a Python function, or, well, when you're dealing with NumPy arrays or any sort of array, it will have, it'll check each access. Is this within the array? Is it valid? And throw an exception, just like Python would if you go outside. You can turn that off. If you trust your code, once you know that it works or think it works, you can turn that off. So that obviously makes it slower, right? If every NumPy access is checking whether it's within bounds, you can turn that off. The other one you'll see is wraparound, because you can access a NumPy array with a negative index, right? And it does the right thing. You can turn that off as well, so that if you're only going to index by positive indices, and you know you're not going to access, or you're pretty sure you're not going to access out of bounds, you can turn both of those off and it makes it much faster. Okay, and we generally will do that. You'll want to do that in most cases. You'll just want to assume that don't start with that. Do that before. Leave it, no, don't turn it off before. Leave the checks in. When you want it to go faster, turn off those checks, and you can compare. So as we said, you can use the GIL to get back into Python functions if you need to print or something like this. All right. Parallel loops, very much like parallel blocks, except for they loop over an index. You give it a number of threads. You can, instead of doing a with no GIL, you can do no GIL equal true. And then it just does a loop. Now as you would expect. So it's very similar. So here's the parallel range example. Oops, let's compile now. Where's my error? Oh. Parallel range. Oh, how many threads? 10 threads, okay. So this one loops 1 to 100. prints out both the index and which thread it was given to. So I told this one to use 10 threads, so we can see 0 through 9. But it loops in, they're in separate threads, right? The loops happen in whatever, basically they'll happen more or less in order. They'll be assigned to threads in that order, but then that thread, depending on how long it takes to actually do the work, may come back and get another index before some other index gets done, and then you get these out of order executions, right? Okay. Variables inside of parallel ranges, inside of loops, are also private to the thread. And at the end of the loop, they're called last privates. At the end of the loop, they're equal to the last iteration. So we had this loop in there. And this one, if you noticed, oh, actually, I added an extra print right here. Basically, what was at the end of the loop, the value will always be the last iteration. So the last iteration was 99, 0 to 100, or range 100, run by thread 9. Okay? That's sometimes useful, but more useful is if you can do reductions automatically as well. If you have in-place operators on a value, for example, you set something like the value plus equal to the index. Now that's obviously a shared variable, right? Or that has to be shared for this to make sense. If it were just last private, then I would get whatever the sum over one thread was, but that's going to encounter some of the values, but not all of them. But Python and OpenMP are smart enough to say, okay, well, this is a reduction over a variable. I can, if it's simple enough, like plus equals, I can explode that out into a very simple sum over the threads, then sum within the threads, then sum over the threads at the end. And so you can do, oops. Oh, no, I was at the right place. There we go. So that, I'm just going to run this example, which is basically just what we saw, sum over the indices in parallel. And it does that in 10 parallel threads, or whatever parallel threads, and gives me the output at the end. So this is useful. This can be quite useful depending on what you're doing. So it's the same as a reduce across the multiple pieces, across the multiple threads, and then coming in together. Does that make sense? What's going on here? Only because I did plus equals. I did an in-place update. And so it writes that as not a private variable. If I'd done an assignment, it would have been private, yeah? And it would have taken on, outside the loop, it would have taken on the value of the last iteration. But because I'm doing plus equals, I'm doing an in-place update on a defined variable, it gets a private copy for each thread. So there are 10 threads going across there, so each of them is going to process about 10 objects. So each one sums up its 10 indices that it encounters, and then at the end, they're summed together. Probably just using the plus equals again, but I think it may actually inspect what operation was used. Okay. Do we need locking for val? No. So that's the nice thing. That's what OpenMP is giving us. The same thing would happen in C code, possibly with some extra hints there. But Python takes care of this for us. It says, you're doing an in-place operation. I will separate out into private variables each of these summations and then combine them at the end for you. So we don't need any locking or anything like that. Okay.
How would the slower code affect what would be the difference?
The slower code, oh, you mean if we were to try and do it, well, how would slower code look if we were to do this without the support?
Without the
Without the in-place. So in that case, it would look something like, with lock, some lock. Right, we'd have to do this. If we didn't have the private variable or, you know, if it weren't private, or if we didn't have this support, you could do something more complicated, right? We could have, you could also do, what? For example, we could make sum an array.
This would be only to close the dot.
Right, this one we wouldn't need the lock until the end, thread ID. We could do something like this, but, and then at the end we'd have to sum those together, but that's what this does automatically.
And if we need like for right now, like in the past one,
Yep, hold on.
so sum is an int, right? So,
Sum isn't it, yep.
so if we are like bigger than the maximum int,
Oh, then, well, if you're bigger than the maximum, it doesn't matter if you're threaded or not, something bad happens. Yeah, it'll overflow and wrap around. But that's gonna happen in the serial code as well. So if we were to overflow sum, sum is, I mean, so integer addition in C is defined on all values. It just wraps around back to 0. And that will do exactly, the value will be exactly the same whether we do this in parallel or in serial. No, and it's not going to turn into a Python integer. You're down in C, it just looks like Python, and you don't have to do as much bookkeeping. Is that clear? Okay. So one thing well, we didn't look at, but in the, actually, let me go back to look at this example. So we can schedule range. Yes, yes. What do you notice about the thread IDs and the index they get? Correct. The first index, the first digit of the index is the same as the thread number. Right? There are 10 threads, 100 indices, and each one, as you look through it, always the same first digit. Because the default on parallel ranges is static scheduling, which means take my loop, chop it up into n pieces, where n is the number of threads I'm going to use, and assign each thread independently its own block, which is why you also see, look at thread, which one do we have a lot of here? 5, well, all of them. And look up until you see the next 7. 79, well, actually, look, 9s, 8s. It's always in order within that subblock as well. In this case, in static scheduling. You see? So thread 7's last output is 79, its next one is 78, and the one before that, 77. So it basically took the 100, the range of 100, chopped it into pieces of 10, and launched parallel threads in order on those indices. So that's because of last private. So you're asking what the output here at the very bottom, last index. So that is printed outside the loop. Let me go to that loop. Right, so we go through the loop, and then this is outside of the parallel range. And because I'm assigning to a variable inside the loop, it's last private. So it's not shared thread to thread, so that's the private part. Last is outside of the loop, that variable will take on the value of the last iteration. So this will always be 99. Well, it'll always be 99. Because we're using the default scheduling, which is static, it'll also always be 999 in this case. Is that clear what happened? Okay. There are other options. You can change it using this schedule keyword to the parallel range. You've got static, dynamic, guided, and runtime. Static is the one we just talked about, pre-assigned equal size contiguous blocks. Dynamic is on-demand Basically, give a small chunk, usually the chunk size, I think, defaults to 1. Give one task to each thread, and then when it comes back, it asks for the next task. And just hands them off in chunk size pieces. You can control how large that is. And then guided is, let's start with large chunks, see how long they take. Not, you know, it doesn't start with the entire block. It starts with something like 5 for each. And then as they come back, it gives them a smaller chunk, basically proportional to the remaining work. This is very useful if some chunks take a long time and some don't, especially towards the end where you want to keep things fed. Right? We want everything busy the whole time. And so if you don't know that your work all takes the same amount of time, you can use guided, which will say, okay, we'll do a large chunk, or reasonably large chunks, but not the whole thing at the beginning. And as they come back, we'll give them smaller and smaller work to make sure we're packing in at the end as much work as possible. And then if you want to play with these different options, you can use runtime. And then it checks an environment variable or a function call to see which strategy to use. And you can change it up and see which one works. A lot of examples, when you look online, will have this nested parallel and p-range. In fact, even on the Cython page for the parallel tools. So you can nest a p-range inside a parallel. The p-range just turns into still a work sharing loop, but the number of threads is determined by that parallel. So you can't declare a new number of threads. It's going to be whatever threads you declared or whatever it defaulted to on the outside parallel. This is very useful though still because you can set up, for example, unshared buffers, or you can have parallel a block of code to set up some sort of work that you're going to need for the loops, and then do the loops. And you get that ability to set up for each thread some sort of private buffer or private variables to use within the loop. You can also nest p-range inside p-range, but it just becomes a regular loop by default. So you don't get any benefit. You don't get basically nested parallelism. If you really want nested parallelism over multiple loops, over 2D loops, whatever, you have to construct the indices and then loop over them in a single p-range and handle it that way, right? So you might concatenate them into a long list of paired indices and then loop over them in a single p-range. You probably don't have to worry about this so much. If it comes up, ask questions. But it's good to know that if you do it by default, you don't get that parallelism at the bottom. That's the case also for if you're working in C. This is not a limitation of Cython. So that we can see here actually. So this is a very simple, again, same sort of thing. We've got the outer loop. It's going to just go 10 threads. I've got a parallel block, so I should see 10 prints of that first part. Then nested loops, over 100 and over 5. And I'll just print out some of them. And we can see from this which threads are doing which index. What's it called? Nested parallel. Yeah, okay. So you can see that, for example, thread 9 is always still handling 90. And then these all happen in order. It's just a regular, the second nested loop, which is 0 to 5, always prints out in order and is always just a single thread, always the same thread. Okay, you don't get that, you don't get extra parallelism or finer grained parallelism. Is that clear, what's going on there? Just assume that nested p-ranges are just a normal for loop.
What's different about the first p-range, the parallel?
So the first p-range will be a work sharing loop, and then if you have something like dynamic scheduling in there, then it could happen in any, basically it could happen in any order almost, right? It'll do the first few, but then after that it's going to be serving out job.
I guess I'm confused, because if you have like the 4 cores and your 4 threads in the parallel thing,
Yep.
why would you need further parallelization inside the loop?
So the question is, why would you want nested parallelism to be finer grained?
Yeah.
So suppose that you've got a 2D array that you want to do parallel work over. So you do a p-range over the rows and then a p-range over the columns. Suppose some elements, not rows or columns, but some elements of the computation are very expensive and some are not. Like the Mandelbrot, yeah, exactly. And suppose they're correlated across rows for some reason. If you parallelize across rows and then columns, and you don't have fine-grained parallelism, then some rows are going to be very expensive, and you're not going to get any, they're going to dominate the computation, right? The rest of it might all finish. And you're not going to get the nice thing that you would expect or hope for, where each element is treated in parallel. And so you get a better spread out of, or a better distribution of work. Does that make sense? So you don't get that second level of parallelism implicitly. So if you want to parallelize across a 2D array, you have to put it somehow into a single loop. So you could loop over, x times y, or I times j, and loop each one independently. And then you'll get parallel behavior, and you can do dynamic scheduling and get a nice distribution of work. Exactly, list of indices, or you want to make it fast, but if you want to parallelize across multiple nested loops, you have to collapse them into a single loop by default. Okay, or not by default, to get that to happen. Okay. There's a threading term called barriers. Barriers are basically things that can't be crossed until everyone is there. At the end of every parallel block and every p-range there is an implicit barrier. All the threads that are working will have to wait until they get there. Nested p-ranges, again, turn into normal for loops, and I don't believe that's the case. But all the threads working within that loop. So nothing will continue, which is why, for example, in that last index example, where it prints out the last private value, it doesn't print that out until everything is done, even if some other thread is the last one to print out within the loop. Everything has to get to the end of the loop, and then it goes on. This makes things a lot easier. Otherwise, you'd have to do some sort of wait synchronization. The OpenMP primitives, locks, and nested locks, which are basically locks that a single thread can ask for multiple times in case it has, for example, a recursive computation. They're all available by the C import OpenMP. They're not very well documented. There aren't that many primitives in OpenMP, in C or in Python. So you can just look at the openmp.txt on GitHub. You just search for that file, and it lists them. It's 2 pages long.
That was the OpenMP lock you were using earlier?
Yep. So that's what this looks like. For the actual locks, it doesn't have semaphores, it doesn't have events, things like that you get from the Python threading environment. It only has locks and then nested locks. And they just look like this. You import whatever you need. Create a lock, initialize it, you lock it with setlock, you release it with unsetlock, you get this locked region in here. You can make arrays of them, and then at the end you just destroy it to free up the resources.
Does the C version of OpenMP have good documentation?
I mean, it's C documentation. Yeah, it's straight across. Yeah, you can. Yes, you can look at the OpenMP documentation in C, and all the primitives are documented there, and it's basically the same. A lot of the OpenMP documentation is concerned with more complex interactions of pragmas. So most of the documentation is about different pragmas and how to manipulate them, many of which are not available in Python, but most of which we don't need. Pragma, so OpenMP uses pragmas for most of the parallel declarations. So the way you write C code for an OpenMP compiler is you write your C code and then you put these pound pragma parallel, for example, around or p range or just parallel for loop or something. You put that as almost a comment before the for loop. And that directs the compiler to make that into a parallel for loop. Okay? Python handles most of that for us without having to do this. But if you look at the C code that's generated by Python, it'll have all those pragmas in there.
So practically, if we wanted to really take advantage of OpenMP, shouldn't we just write C code then and then like wrap it with Python?
So yeah, so the question is, shouldn't we just write C code? Then you have to write C code, right? This one, again, you can write Python, add some types, and then get parallelism, and you can make sure it works first, and you can write the sort of the more dense, high-level language in the first iteration, which is a lot easier. I mean, eventually you could translate to C, but you're not going to get, this is the other thing, you're not going to get that much faster. You can write a bunch of C code, you can write some Python code, and then a bunch of C code. They're going to be roughly equivalent. You might get slightly faster on the C code because you have finer grain control, but you're not going to get that much. You're going to get 80 to 90% of it just going this way.
Can't like pure C code in Python and have it work or something, right?
I mean, this is maybe a longer discussion, whether or not you can write pure C code. So you can't write pure C code in Python. You can write pure C code in a header file and include it very easily into Python. You almost never need to, depending on what sort of work you're doing. It almost always turns into very close to the original C anyway. And you can look at it, you can see that it's, the variable names are ugly because it's compiler written code, but it's still pure C code. Okay. That's basically it. You have enough now that you can go off and you can shoot yourself in the foot 100 times in parallel. It's very efficient. You can build on the examples here. There'll be at least 1 or 2 problems in homework 2 that involve using the parallel constructs. All right, next time we'll have the reading discussion about the scalability thing. And then I was thinking for homework problem 5, related to this discussion, connecting components, I have some single-threaded code that's reasonably performant. I'm happy to publish this, and I was thinking I would publish it and then set up a leaderboard. You send me new code, I'll run it on data sets, possibly larger ones, and then I'll just update. This person has the fastest code for this problem. That could be open code, we could publish, you know, we could link it, you know, like Kaggle, where you have to publish your code in some contest, or it could be hidden, it's a secret, my secret sauce, unknown. Show of hands, who would do this? Who, if there were a prize, who would do this? Sense of accomplishment. No, I don't know yet. I was discussing with the TFs. I think it would probably depend on how many people do it, so it could get better and better, right? Sort of like a gambling thing. Come on, put them high. Who would do this? Who hated problem 5? Wouldn't you like to like kill it? You should compete. All right, I'll publish this code then, and we'll figure this out, and I'll get some other data sets to run it on as well. And maybe we'll do this with a few other interesting problems as well. I'm not gonna run it, no, this is code for a single core. Well, you can use, so my code is single core native code. Python code, actually.
You mean it's sequential?
It's, what?
You mean it's sequential or?
My code will be sequential. It'll be in Python, it's not complex. It's very fast, like this paper. I will give that to you. You can do whatever you want within the bounds of Python and C and what you can get it to do. I would prefer Python, right? You can make it parallel. You can use AVX instructions. You can, you know, whatever depth you want to go into. You know, in the future, you could use CUDA. And whatever you do, I'll run, as long as it doesn't have like calls to like bash, you know, remove all my files. If you do that, I'll catch you. And if I had my files, I would know who you were. But I'll post a leaderboard on this, and I'll get some larger data sets that should still fit in memory. Spark, no, I wouldn't use Spark if you want to win this contest. I'll put up the Spark numbers too. They won't be good.
How long does it take to run?
Do you want to know? So the loading time takes about, on the problem that you solved, loading time is around 10 seconds, and processing time is around 2.
2 seconds.
On the Wikipedia data set.
2 seconds or 2 minutes?
2 seconds.
Oh,
2 seconds.
AWS.
Yeah, so this paper, like I wish I had seen this paper before. I would have still made you do Spark, but we would have done a much larger problem. Then again, that would have been much harder. And it would have been, you know, there's still problems that Spark are good. That's a discussion for Wednesday. Okay. I'll put out the code this weekend. You know, you can hate on problem 5. I'll give extra credit for well-named submissions. Yeah, like, you know, style points are available. All right, sound good? All right, see you Wednesday.